SpaceX just pulled off something that left China's space program speechless. While their Long March rockets take months to assemble, Booster 19 went from empty bay to fully stacked in just 28 days. That's 6 times faster than Booster 18's 175-day build and crushes even their previous record of 3 months. How did SpaceX achieve what seemed impossible? And what does this mean for the global space race when one company can outpace entire nations? Let's dive right in. The Starbase team didn't just move fast, they executed a plan that rewrote the rulebook. Booster 19's stacking happened in December, exactly on schedule, despite replacing the damaged Booster 18. While traditional aerospace companies would have seen this as a catastrophic setback, SpaceX treated it as just another Tuesday. The secret? Version 3 wasn't designed to be revolutionary. It was designed to be buildable. Here's where it gets interesting. The gas manifold system that used to require workers to crawl into cramped stainless steel spaces has been completely relocated to the booster's exterior. Now it snaps together like industrial Lego blocks. The Raptor 3 engine tells an even bigger story. Gone are the bulky heat shields, exposed piping, and external hardware that made earlier versions look like steampunk machinery. Everything's tucked inside the structure now. No loose wires, no external tubes, no armor plating. What does this actually mean for production speed? With fewer exposed components, SpaceX's robotic welding systems can now produce multiple Raptor 3 engines per day. Fewer parts equal fewer failure points and faster quality inspections. By early December, they'd already tested Raptor 3 serial number 75, with number 76 spotted soon after. That's dozens of engines built and fired before Booster 19 even finished stacking. But the real question is, can this pace actually be sustained, or is this just a one-time push for Flight 12? The data suggests something far more significant. Booster 19 still faces completion work, integration, and extensive testing before it's flight-ready. Cryo tests are scheduled for the first week of January. If those pass, engine installation follows, with a static fire potentially happening by mid-January. The raceway assemblies, grid fin integration, and final engine mounting are all running in parallel. SpaceX isn't just building fast, they're building smart, with overlapping workflows that would make traditional project managers nervous. Now look at the design changes themselves. Booster 19 features an asymmetrical layout that's immediately visible. The chines, those aerodynamic extensions along the body, are now positioned specifically for improved gliding performance during the return flight. Even more striking, this booster has only 3 grid fins instead of 4. Why remove the upper fin? Because during descent, it would have caught turbulent air, creating control problems. These aren't cosmetic tweaks. They're calculated adjustments that improve downrange control, allowing the booster to travel farther on its return path while burning less fuel. How much fuel are we talking about saving per flight? The integrated hot staging ring represents perhaps the most underrated upgrade. Previous designs required this ring to be swapped out after every single flight. Hours of labor, inspection time, and potential points of failure. Now it's permanently built into the booster structure. This alone could shave days off the turnaround time between launches. When you're planning hundreds of Starship flights per year, days become weeks, weeks become months. The compounding effect is massive. Ship 39 tells its own parallel story. Fully stacked inside Megabay 2, it's awaiting final assembly work before its first cryogenic test and static fire. The open Megabay doors signal the team is close to testing phase. The completed heat shield system is visible from outside, a strong indicator that major assembly is finished. But here's what makes Ship 39 special. It's not just another prototype. It's the everything tester. This vehicle will validate payload deployment systems, demonstrate in-space fuel transfer, and prove out the new heat shield design under real re-entry conditions. All of this feeds directly into SpaceX's 2026 objectives. long-duration orbital flights measuring fuel boil-off rates, in-orbit refueling trials, and deploying Starlink V3 test satellites. Ship 39 carries the weight of an entire development roadmap. Can one vehicle really validate that many critical systems? The answer lies in S39.1, Ship 39's dedicated test tank. This unglamorous piece of hardware already completed the cryogenic and structural validation tests needed to confirm version 3's design upgrades. Instead of rushing the flight vehicle straight into testing, SpaceX ran parallel validation programs. S39.1 absorbed the risk, proving each system separately before integration into Ship 39. On December 22nd, S39.1 was spotted moving from Sanchez to the Star Factory nose cone hall for continued work. The testing never stops. But there's a bottleneck. On December 19th, a new vertical gantry structure started rising at Massey. This appears to be SpaceX's response to the Ship 36 explosion damage from June 2025. The new infrastructure will support Starship testing with improved platforms for fueling, maintenance, and inspections. Until it's complete, Ship 39 might wait, even though the vehicle itself looks ready. This is the unsexy reality of rapid development. Sometimes you move so fast that your infrastructure can't keep up with your hardware. Flight 12 is currently targeting a launch window between February 1st and 7th, 2026. The mission profile mirrors previous flights, but with a crucial difference. This debuts the new Block 3 vehicles and the second orbital launch pad at Starbase. The upper stage will perform a controlled re-entry and splash down in the Indian Ocean, collecting data on heat shield performance and atmospheric descent behavior. The flight path stays suborbital, falling just short of a complete orbit. Why not push for full orbital on the first Block 3 flight? Because SpaceX learned from the Apollo era's mistakes. They're validating systems incrementally rather than attempting everything at once. Flight 13 and beyond will target full orbital flight and potentially the first attempt to catch both booster and ship with Mechazilla's arms. The progression is methodical, even if the pace feels breakneck. The manufacturing evolution becomes obvious when you compare Starship V3 to the Mark I prototype from years ago. The surface quality alone tells the story. Advanced robotic laser welding replaced rough manual techniques. Precise lasers now melt and fuse steel pieces together, creating flawless joints without bumps or weak spots. The shaping process is equally refined. SpaceX starts with cold-rolled 304L stainless steel sheets, stamps them into large ring sections, then uses giant planisher hammers to flatten the welds until they blend seamlessly with the surrounding material. The choice of 304L stainless steel itself is strategic. It doesn't rust, handles cryogenic temperatures without becoming brittle, and maintains that signature polished finish. But the real game changer is the Mega Bay transformation. Over the past few years, its interior has been completely rebuilt with new work platforms, turntables, and advanced tooling systems. This isn't just faster production, it's industrial-scale manufacturing of spacecraft. What's coming next makes the current pace look slow. By June 2027, SpaceX plans an uncrewed lunar landing with the HLS Starship. That's around the same time frame NASA originally hoped for Artemis 3. If that test succeeds, astronauts could follow just 1 year later, touching down on the moon by September 2028. But that uncrewed flight represents something far bigger than just a lunar landing demo. It's the first full-scale orbital refueling test, the keystone technology that unlocks everything else. The architecture SpaceX is developing revolves around 3 elements working together in low Earth orbit. First, the depot ship, a massive orbital storage tank holding around 1,200 tons of propellant. It's designed for long-term orbit, so it doesn't need re-entry hardware like flaps or heat shields. Second, the tanker fleet, reusable starships dedicated to ferrying propellant from Earth to the depot. Each tanker carries roughly 100 to 150 tons per flight. Their reusability makes the economics work. Third, the mission ship, the Starship that actually goes places. Once fully fueled at the depot, it performs translunar or trans-Mars injection burns, setting off for destinations across the solar system. Here's where the numbers get staggering. To fully fuel a mission ship might require 10 to 20 separate tanker flights. Each tanker tops off only about 15% of the main ship's propellant capacity. A single Starship carries roughly 200,000 gallons of fuel, more than twice the mass of the entire International Space Station. But volume isn't the real challenge. It's what's inside those tanks. Starship runs on liquid methane and liquid oxygen, cryogenic propellants that must stay at extremely low temperatures. This makes them far harder to handle than the hypergolic fuels used on ISS. Then there's the microgravity problem that nobody talks about. In orbit, without gravity, liquids don't settle. Fuel clings to tank walls while gas bubbles float to the center. Standard pumps would just suck gas instead of liquid. So how does Starship solve this? The solution is surprisingly elegant. Instead of complex pumping systems, Starship uses small ullage thrusters. These fire briefly, giving the ship a tiny push that settles liquid fuel to the tank bottom. Then, internal tank pressure squeezes the propellant through the transfer lines, pushing it smoothly into the receiving ship. No pumps, no gas bubbles, just physics. But even with that solved, there's the boil-off problem. Cryogenic fuel evaporates from any heat exposure. Tanks need heavy insulation, and refueling flights must happen frequently to replace whatever boils off in orbit. This entire architecture marks a turning point. For decades, orbital refueling was considered too expensive and too complex to be practical. What changed? Reusability. With Starship's rapid turnaround, the economics finally work. The idea isn't new. NASA dreamed of Earth orbit rendezvous back in the 1960s. The plan was launching multiple smaller rockets, docking them in orbit, refueling, and assembling a spacecraft larger than Saturn V. But the technology couldn't handle it. Pumping liquid fuel in zero gravity was unreliable, docking was risky, and the cost would have been astronomical. So NASA shifted to Lunar Orbit Rendezvous, one Saturn V carrying both the command ship and lunar module. It was cheaper and faster, but there was a trade-off. Apollo became a short-term flag-planting mission. Total material return from all missions was just 382 kilograms. No permanent base, no rovers, no infrastructure for future missions. Now, more than half a century later, with reusable rockets and orbital refueling, we can finally execute what Apollo-era engineers could only sketch on paper. But why does SpaceX insist on refueling in low Earth orbit specifically? 3 strategic reasons. First, energy efficiency. Launching fuel to LEO takes far less energy than sending it directly to higher orbits or deep space. Each tanker flight can carry more propellant per launch. Once fully fueled in LEO, a Starship can perform massive burns to reach distant destinations. Second, safety and debris mitigation. If something goes wrong, an explosion, a propellant leak, the lower altitude means debris won't stay in orbit for decades. Atmospheric drag will pull it down where it burns up harmlessly. Third, LEO serves as the perfect departure point. Every deep space mission will first reach low Earth orbit anyway. It's the perfect pit stop before leaving Earth entirely. And that's exactly what makes SpaceX's 28-day build time so significant. This isn't just about assembling metal faster than China or anyone else. It's about achieving the production rate needed to make orbital refueling economically viable. Without rapid manufacturing, the entire depot architecture collapses under its own weight. You can't run 10 to 20 tanker flights per mission if each booster takes 6 months to build. This is where SpaceX's strategy becomes crystal clear. Every design simplification in version 3, the external gas manifolds, the cleaner Raptor 3 engines, the integrated hot staging ring, exist to support one goal: sustainable, high-cadence launch operations. While other space programs celebrate annual milestones, SpaceX is building infrastructure for weekly Starship flights. The 28-day booster isn't a publicity stunt. It's proof of concept for an industrial model that will enable permanent human presence beyond Earth. The Apollo program planted flags and collected 382 kilograms of moon rocks. The next era will build fuel depots, land permanent bases, and establish interplanetary supply chains. And it all starts with manufacturing speed that makes traditional aerospace look like a historical reenactment. So what's your take on this new space race dynamic? Can China catch up to SpaceX's production pace? Or is the gap already too wide to close? Drop your thoughts in the comments below. If this breakdown gave you new perspective on what SpaceX is really building, hit that like button and share this video with anyone tracking the space industry. And subscribe to Space Update 24 hours so you don't miss our coverage of Flight 12 when it launches. We'll be here breaking down every detail. Thanks for watching.